Hello everybody, now we will start our lecture. So lecture number 2, systems of differential equations. We will discuss systems of differential equations and we will start with the definition. Okay. System of differential equation. I will use the abbreviation of differential equations. I will abbreviate it with these two letters, differential equation. So is a collection of equations. It will be the first order differential equations of the form x1 prime equals f1 depending on two variables t and x1. So be careful. From now on, we will use the letter x for unknown function and t for an independent variable. So x of t will be our solution. x2 prime equals f2 of t. So not only x1, xn. There will be n variables. First order differential equations. Our functions fi depend on n plus 1 variables. And all the functions will be considered as real valued and continuous functions. So each function for each I is a continuous real valued function. Depending on n plus 1 variable and n plus 1 variables. N plus 1 variables. Okay. And to simplify this notation, we will use the vector notation for the system of differential equations. So if we consider a vector, if we consider x1, x2, and so on, xn as coordinates of a column vector, so we will if we consider a vector with coordinates x1 and so on, xn, and if we consider a vector-valued function, f vector, it depends on t and x, is a vector-valued function. So now we can see that f is from Rn plus 1 to which space? What is the dimension of the space? The image of this function f is n-dimensional. You can see that there are n components, right? N coordinates of our vector f, right? So to Rn. So n plus 1 is a number of variables of the function. So we have n plus 1 places for variables, right? And the output would be the n vector. So it is from n plus 1 to Rn. And then in this case, we can rewrite this system in the vector form, so more concisely in the vector form. Okay, it will be x bar prime equals the vector f, the vector value of function, depending on n plus 1 variables. So this would be the concise notation. And sometimes I omit the vectors, the bars above the variables, right? Sometimes I will write it in this form. So not bar, but you should remember that we have the vector, so the vector equation, right? We have, so by this or by this, we mean this system of differential equations. Okay, is it clear? I hope so. So now we will discuss systems of differential equations of the first order. Okay, so these systems generalize all we know up to now. For example, so this is the remark. On the preceding seminar and the preceding lecture, we have discussed the differential equations of the form, let it be y n equals f of let it be t y prime and so on, y n minus 1. Okay, I claim that this system generalizes this nth order differential equation. How can we rewrite this equation as the system of the first order, as the system of differential equations of the first order? Is it possible to rewrite this as the system? The answer is yes. We can introduce new variables if we denote, redenote y by x1. So let x1 be equal to y. Okay, then x2 is y prime, dot dot. Then xn minus 1, well, yn minus 2. Xn would be the nth derivative. Then we can rewrite this differential equation as the system of n differential equations of the first order in the following manner. So we can see that x1 prime, what is x1 prime? Look at this notation. So x1 prime is equal to y prime. Yeah? Y prime, but y prime is x2. So it is equal to x2. This will be the first equation. The next equation, x2 prime. What is x2 prime? x2 prime is y2 primes. But y2 primes is x3. Dot, dot, dot. And then the last equation would be xn prime. So, not correct then. So I will remove this. So we need not this, right? Xn. Okay. It is xn is y n minus 1, right? And xn prime is equal to the nth derivative of y, but nth derivative of y is here, f of t, then comes x1, x2, dot, 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 x n minus 1. And xn, right, because this is xn. This is xn. So this equation can be rewritten as a system. But converse is not true. Not any system of differential equations can be rewritten as just one differential equation of the greater order. For example, if we have something like x prime equals 2x, y prime equals y plus t, we can't form just one equation, one differential equation of the second order. So we may go from the from one equation of the nth order to the system of differential equations of the first order. Okay, is it clear? Right. So if we study this system or this vector equation, if we discuss this, we would be able to study the properties of the differential equation of the nth order in particular. Right? Let's discuss this system. Okay, now I want to discuss the existence and uniqueness theorem. It is called, so our goal is to discuss the existence and uniqueness theorem. So it is known by the name of well, just a moment. So the name okay. So we will discuss the Carl Lindelof. Just a moment. Lindelof. Okay. Theorem. But before we discuss this, I want to introduce some notions that we would need in the future. Okay, so this is our equation. So let it be equation number 1, vector equation.
Equation number 1, why didn't we
have okay. Thank you. This is equation number 1. Well, and we will consider the function. So I recall that this is the function from Rn plus 1 to Rn. But sometimes f is defined not in the entire Rn plus 1, but in some open subset of Rn plus 1. So we will consider D to be an open, so is an open subset of Rn plus 1. So f would be defined in D, so from D to Rn. Sometimes it is not defined in the entire space Rn plus 1. Right? So D would be our domain of the function. Okay? And I'd like to recall that vector function f is continuous and real value, so is continuous in D. Well, okay, so we will be interested in the solution of this differential equation. What is a solution to this equation? Okay. So a function x so x must depend on one variable t, right? What is x? Is a vector x1 depending on t, right? Dot, 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 xn depending on t. So x must depend on one variable. And so we say that x is from some interval ab to Rn. This function is called a solution to 1. Okay, if so the points tx is in D for any t from the interval AB, then requirement number 2, x must be differentiable and it must satisfy equation number 1. So it must be f prime of t would be equal to f of tx. For so AB is a subset of the real line. AB is the interval. AB. So differentiable and of class C1. We can see that it is of class C1. So what does it mean, of class C1? Do you remember? What is the class C1? Which functions are called functions of class C1? They must have derivative. A function is of class C1 if it has a derivative, and this derivative is continuous. Continuous derivative. Okay, so if we speak about a vector valued function, then we should claim that each coordinate, each component of this vector function must be of class C1. Right, and we can see, so since we so if we require that the function is continuous, so you can see that the derivative, any component must be continuous. Well, so this is a solution, and we will consider, in what follows, we will consider the initial value problem. So initial value problem. I recall that the initial value problem, so I will omit this, right? X0. It looks like this. So it's system number 2. So T0 X0 must be in D. So by x, I mean the vector valued, the vector, right? I meet the bar above x, no, x0. And okay, t0, x0 must be in D. And then to solve the initial value problem means to find a solution such that it satisfies this requirement, and in addition, it should satisfy this initial condition, right? The solution of the initial value problem is a function which is a solution and satisfies this requirement. The initial value problem. We will discuss the initial value problem. Okay. So there is the Picard-Lindelof theorem. This is the theorem of the existence and uniqueness of the solution. It was partially proved. It was proved during the spring semester in the previous year, and for the functions of one variable, not for the vector equation, but for so for one first order equation. So now we will discuss this theorem. So we will have a seminar where this theorem was will be discussed, right? And I will need the following lemma. So we used this lemma in the preceding semester to prove the Picard-Lindelof theorem. So the lemma was the following. So I will state this lemma and I will show how to prove it. Okay. So it says that the function x of t is a solution of 2 if and only if, so this initial value problem, if and only if we have the following for any. Okay, so is a solution of 2 on the interval. Just a moment. A, B containing T0. So the interval containing T0. So this means that x. So given an initial value, it's T0. This is x0. Hello. So, but the solution is given on the interval AB, containing T0. Okay, if and only if x of t, so for any t from the interval AB, x is equal to x0. So let it be bar. Okay, plus the integral from t0 to t f of s x dx. So now this lemma is the statement about the vector functions. It was proved for some scales, for for scalar function, right? For function with one coordinate, right? For just the function depending. It was proved for the function from R to R. It was proved, but now it is stated for the vector valued function. Okay, but proof is similar. Proof is similar. Okay. So there was a requirement for the function f. It must be continuous. So the function in this formula is continuous. And so the Riemann integral from t0 to t, so on any segment of the continuous function exists, right? So because this function is the composition of continuous functions. Now, and now let it be, so suppose x is a solution, let x of t be a solution. Then let's consider the difference, which is equal to x of t minus x of t0 . So it is equal to the integral from t to t0, from t0 of t of x prime of s ds by the fundamental theorem of calculus. But we know, so that if we know that x of t is a solution, we can replace this by the function f, right? And it will be the integral from t0 to t f of s, x of s, because x prime is equal to the function f ds. So it is proved, conversely, if x prime of t, so if x is equal to x0 plus the integral from t0 to t f of s x of s ds, then we check that x of t0, what is x of t0? So if x of t satisfies this, then if we substitute t0 for t, we have the integral from t0 to t0, and this integral will be equal to 0, right? So I will write it plus the integral from t0 to t0 f of s x of s ds. So this is 0. So it is equal to x0. Well, and let's find the derivative. What is the derivative of this? So if we differentiate, take the derivative with respect to the upper limit, what would be, what we will obtain if we take the derivative of this with respect to the upper limit? So this function, right? And this proves, so of t, of course. So we can see that the first equation, this equation is satisfied, and the initial value, so and x of t0 is equal to x0. So so we can see that x of t is the solution of the initial value problem. So this lemma is proved, and we will use it in what follows. We will need it. Now I will state Picard-Lindelof theorem, but I will not prove it. The proof is very complicated, and so I think, and I proved so the part of the theorem. So I proved the uniqueness of the solution, but for in the vector form, I will only state this theorem without proof. Okay. We'll study it without proof. Okay. Now I will clean this. Or maybe I will use this part of the blackboard. But it seems to me that I need one more notion to state this theorem. So we will start with it. So we are discussing the initial value problem of the form x0, the initial value problem. Okay, and to state the Picard-Lindelof theorem, we will need the definition of the Lipschitz condition. Okay, so the function f from Rn plus 1 to Rn. So I recall that the vector function depends on t, x1, and so on, xn. Depends on n plus 1 variables, including t. Satisfies the Lipschitz condition condition in x, not in all the variables, but only in x, in the domain, okay, in the domain D, if there exists a constant L, it is from R, a constant, such that for any x and y, from any 2 points x and y from D, so not from D, but for any x and y such that tx and ty, because D is n plus 1 dimensional, so they must be from D. So for any 2 points such that tx and ty are in D, are both in D, we have the following. The norm of f of tx minus f of ty must be less than or equal to L times the norm of x minus y. Okay, so this is the Lipschitz condition. F satisfies the Lipschitz condition in X. So pay attention to this. So T is fixed. It is the same for both points. Only X and Y are varied. Okay, so this is the Lipschitz condition. Now let's try to discuss this Lipschitz condition. Let's discuss Lipschitz condition. Okay, and so we need to discuss two problems. First, is it possible for a non-differentiable function to satisfy Lipschitz condition? And now I will give an example. Let's consider a function. Let the function be, let it depend on t and x in the following way. Let it be, for example, t cubed plus the absolute value of x. Let's check whether this function satisfies Lipschitz condition. And so we need the domain D, let it be R2. D is equal to R2. Let's check whether this function satisfies Lipschitz condition. To do this, we need to consider the difference and the absolute value of the difference. Okay, so what is the difference? Let's start with the difference. What is the difference? Okay, t is the same. And so t is cancelled out, and we have the absolute of the absolute value of x minus y absolute. Now, our goal is to discuss the absolute value of this difference, right? What does it mean? So it is the norm of the vector, the norm of the vector. Do you remember how to compute the norm of the vector, of a vector? So the norm of x, for example, there are several ways to introduce the norm, but our usually it is defined as the square root of this sum, right? Okay, but in our example, it is one-dimensional, right? So x is from R1, and so the norm would be the absolute value, just absolute value, right? So we need to estimate the absolute value. Is it true that it is less than or equal to the absolute value of x minus y? Is it true or not? Do you know? Just for numbers. So we can check it directly. So consider, for example, several cases. So x is positive, y is positive. Then they are equal. X is positive, y is negative. Then this is less than this. Or we can instead use the triangle inequality to prove this. How can we do this? So by triangle inequality, we have that, for example, absolute value of x is less than or equal to x minus y plus y. By triangle inequality. Then if we move the absolute value of y to the left, we will get this. From the other hand, we can prove that conversely, y minus x is less than or equal to x minus y. And from these two inequalities, it follows that this is true. Right? Well, so this is true, and is it true that we are done? Have we proved that this function is Lipschitz? Is it true that this function is Lipschitz? Does this inequality prove that our function is Lipschitz or not? Lipschitz. Yes, yes, it is Lipschitz, because look at this definition. Look at this inequality. Well, it is, so our inequality is a particular case of this inequality with L equals, what is L in our inequality? What is L? 1, right, correct. L is 1. So it is Lipschitz. However, x is not differentiable. However, this function is not differentiable in x, right, but it is Lipschitz. And in what follows, we will prove that any C1 function is locally Lipschitz. But now I will give an example of a function which is not Lipschitz. Okay. Example number 2. Let's consider a function which is equal to x to the power 2/3. And d will be, let it be r. So r squared. Then let's check the condition. Let's check the Lipschitz condition. So we need to consider the difference for any 2 points x and y, and the absolute value is equal to x to the power 2/3 minus y to the power 2/3. Okay, I want to prove that f is not Lipschitz, and I will consider y to be equal to 0. Let's consider this point. Then, in this case, f of tx minus f of t0 will be equal to x to the power 2/3 okay. If it were Lipschitz, it would satisfy inequality. Which inequality? If it were Lipschitz, then it is less than or equal to some constant L multiplied by x. So x minus 0 is x, right? If it were Lipschitz, it would satisfy this. But we have that it is equal to x to the power 2/3. If we represent it in the form of 1 over the absolute value of x, so in this, can we rewrite this in this form? Is it true? Then we can see x, and I can see that if x approaches 0, then this coefficient 1/3 approaches infinity. This means that so there is no such constant L, right? There is no such L that this is satisfied because this coefficient, it is equal to this, and this approaches infinity as x approaches 0. Okay. So this proves that our function is not Lipschitz. So this function is not Lipschitz. Okay. Now we have no much time, so I think I state lemma without proof because we need to prove two other important statements. So I will state a lemma without proof because we have no time to prove it. So it takes time. Lemma 2 is this. So if the function f from D to Rn okay, so has partial derivatives. So just a moment. Not has partial derivatives. So is differentiable. In x and partial derivatives. All the partial derivatives. So this is the vector function. So we have partial derivatives. If they are bounded, let it be D. So in D, so and D is convex and open. So maybe we need not. So open. So we consider the open set. So we need not. I think we need not state that D is open. So D must be convex, and partial derivatives must be bounded in D. So then f is Lipschitz in x in D. Okay, so if the function is differentiable, then it is Lipschitz. But not all Lipschitz functions are differentiable. For example, this function is not differentiable in x, but with respect to x, but it is Lipschitz. And now they pick our Lindelof theorem. Says that if the function f vector function f is continuous locally Lipschitz in D, which is an open set. Now D is an open set. Then for any initial value t0 and x0 from D, there exists the interval a b containing t0 such that the solution of 2 exists and unique on the interval AB. Right. Yes, this is the Picard-Lindelof theorem. Right. The function must be continuous Lipschitz in D. In X. Okay, so in D and in X, right? In X. In D. Open set. Locally Lipschitz, what does it mean? So we spoke about the Lipschitz function. What does it mean locally Lipschitz? This theorem is local, right? Local. So the solution exists and unique locally near the point T0, right? And so we may speak about locally Lipschitz functions. So this means that for any fixed point, this one, there exists an open set containing this point such that our function is Lipschitz in this open set. So this means locally Lipschitz. There exists a set of open sets containing this point in which our function is locally Lipschitz. Is Lipschitz, right? Then it is locally Lipschitz. Okay, well, and so is it true that we need to check, so given a function, check whether or not the function is Lipschitz or not. So sometimes it is difficult to check the Lipschitz condition. It is difficult. So to write down this inequality, to try to find L and so on. But if our function is of class C1, then it is locally Lipschitz. If f is of class C1 in the variable x, then it is locally Lipschitz, right, by this theorem. So the class C1 means that these partial derivatives are continuous. If they are continuous, they are bounded in some closed subset, right? So by the Weierstrass theorem, any continuous function, so this, for example, right, it is continuous. And if we want to check whether our function is locally Lipschitz or not, so we can choose a ball, let it be a closed ball, so with a boundary, containing a boundary. Then these partial derivatives, if they are continuous, they must be bounded. And so this requirement is satisfied. And so this proves that our function is locally Lipschitz. So this would be a corollary. Corollary. If our function is of class C1 in X, then and this is and we can continue in this way. Then for any point T0 x0 from D, there exists unique solution. Locally, of course, on the interval containing T0. Well, this is a corollary, and usually we will use this corollary instead of this theorem because it is more simple, it is more easy to check whether our function is of class C1 than to check whether it is locally Lipschitz. But this statement is more general, right? Locally Lipschitz functions, for example, the absolute value is a locally Lipschitz function, but not C1 function. Okay, so remark. If our function is continuous, but not locally Lipschitz, it can be proved that the solution exists, that the solution of the initial value problem exists, need not be unique. And now we will consider example 3. Example 3, which is the continuation of the example 2. Of the example 2. We have considered, I'd like to recall that we have considered the function which is equal to x to the power 2/3. Let's try to solve the equation x prime equals x to 2/3. And let's consider the initial value problem, x of 0 equals 0. So this initial value problem, let's try to solve. It can be solved directly. So the variables are separated. X over 2/3 equals dt. But we have lost a solution, x equals 0, right? Because we divide by x, we have divided by x, and so we have lost a 0 solution. Well, but just x equals 0 is a particular solution. Is a solution. Then let's integrate parts. We have x to 1/3 equals t plus c. Then let's solve for x, and we will get x equals, so it would be, so divide by 3 and then raise to the 3rd power. It would be 1 over 27 times t plus c cubed. And so we have a solution, so this solution. But now let's turn to our initial value problem. So we have this condition. And if we satisfy, if we substitute 0 for t and 0 for x, we will get 0 equals 1 over 27 times 0 plus c cubed, from which we have c equals 0. And so the answer is x equals 1 over 27 t cubed. Is a solution of the initial value problem, this one. And at the same time, we have a solution which is x equals 0. These are two solutions to this initial value problem. So this or this, they are both solutions. So the solution is not unique. If we sketch the graph, we can see that this is a solution. So it is t and this is x. So the solution should go through this point. The solution x equals 0 is this straight line. And this is the cubic parabola. This is also a solution. But we can prove that there are infinitely many solutions going through this point, because we can construct, so for, we may start from here, next go in this way and continue our way in this way, right? So this is also a solution for some values of c. So a function which can be written as, so let it be minus c1, and if this is c2 and this is minus c1, then if I define x of t as 1 over 27 t minus c1 cubed, if t is less than c1, so plus c1 is positive, c plus minus c1, then 0 if t is from minus c1 to c2, and 1 over 27 t plus c2 cubed if t minus, if t is greater than or equal to c2, then this is also a solution to the same initial value problem. So there are infinitely many solutions to this initial value problem. But let's check whether the hypothesis of the Picard-Lindelof theorem satisfied or not. Let's check whether the hypothesis, whether or not the hypothesis is satisfied, right? Maybe this example contradicts our Picard-Lindelof theorem. Does it contradict the theorem or not? Is this function locally Lipschitz or not? So this function is not Lipschitz, because this is the continuation of the example 2. In example 2, we have discussed this function and we proved that it is not Lipschitz. This is not Lipschitz function, and so it doesn't contradict, because the hypothesis of this theorem doesn't hold for this function. Right? So it doesn't contradict. Well, now we have not much time, but I want to, so our next goal is to discuss the dependence on the initial values. So I want to change, so look at this initial value problem, and we may change the point. We may change x0 to some other value, x1, x2, to some value which is close to x0, and we want to investigate how the solution will change. So we want to compare the estimate of the absolute value of the difference. So the difference between two solutions when we go away from the initial values. So dependence of the solutions on the initial value, on the initial values. Well, and to do this, we need the Gronow's lemma, and now we will prove the Gronow's lemma. It is a very useful tool in many proofs. It will be used in what follows, so it is very important, and I want to prove it. It is called the Gronow's inequality. Gronow's inequality. Okay. Let u from a, b to r be a continuous function. Such that there exist two constants, c and L, which is greater than or equal to 0. Okay, such that u of t is less than or equal to c plus L times the integral from t0 to t u of s ds, or from not t0, so it is from a to b, a to b. Then okay, u of t is less than or equal to c times e to the power L, so of t, so t minus a. It will be used. Now I will prove it. So for any t from a to b. Now I will prove it. To prove this lemma, I will introduce the function f of t, which is equal to c plus L times the integral from a to t u of s ds. So let's introduce this function. Let's find the derivative of this function. If we differentiate this function with respect to the upper limit, we will get u of t, right? Just take the derivative of this integral with respect to the upper limit. And we have this inequality, so we have this, right? U of t is less than this, right? So we can apply, I will move to this part, f prime of t, this part of the blackboard, equals u of t, but by the hypothesis, it is less than or equal to c plus L times the integral from a to t u of s ds. Okay, so it is not u of t, of course, right? It should be multiplied by L, because L is the constant, right? So L is the constant, and then we differentiate with respect to t, and we will get this u of t times L from this integral, right? And so we must multiply this by L. But this is denoted, it was denoted by f of t. It is f of t. So we can see that it is L times f of t. So we have the following inequality. F prime of t doesn't exceed L times f of t. Okay, let's move this to the left-hand part. Minus L times f of t is less than or equal to 0. Now I want to multiply this inequality by the integrating factor, factor of e to the power minus L t. Then we have the following: e to the power minus L t f of t minus L times e to the minus L t f of t. And we can see that this is the derivative of the function e to minus Lt times f of t Can you see this? So the derivative of this product is just the same as this expression. Right? Is it clear? So the derivative is this. So we can see that the derivative of some function is less than or equal to 0. So it follows from this inequality that the function is decreasing, non-strictly decreasing. E to the power minus Lt times f of t is a decreasing function. So it is decreasing on AB, but we know that at the point A, it takes the value of e to minus LA times f of A, right? And so since this function is decreasing, we have the following: e to minus Lt times f of t is less than or equal to e to the power minus LA times f of A. Okay, is it clear? Do you agree? Okay, so what is f of A? Can we compute f of A? F of A, what is f of A? Look at the definition of our function. This is our function. What is f of A? So we must integrate from A to A. So this integral would be 0, and so f of A is c. So it is equal to c. Then e to the power minus Lt times f of t doesn't exceed c times e to the power minus La. And then after all, I will multiply by e to the power Lt. I will multiply both sides by this, and I will have f of t is less than or equal to c times e to the power L t minus A. Well, Okay, what about u? So u of t. Let me see. Okay. Well, so you can see that u of t is less than this. So u of t is less than, right? Is less than this function. This. Oh. Right, it is less than or equal to f of t by the hypothesis, right? And it is less than or equal to c times e to the power L times t minus a. So it is proved. Okay, so we need to prove one more thing. It is, I don't know, maybe we can do this. So I want to use this this inequality, right, for okay to prove multiply by t here, by L. So to finish this idea, I need to prove one more thing. But so this is the end of the lecture. What shall we do? So why can't you come to the lecture in time? Right, so we have lost several minutes, but now we need these minutes to complete the lecture. So this is the problem. So you should be in time, please.
You can punish us and finish the
Well, maybe we will finish the proof, right? And then after this we will have a break, right? Maybe let's do this. So this is the Gronal lemma, and we will use it in proving the following theorem: the dependence on the initial conditions. So we will consider the theorem. So I will state, first of all, I will make some preparations for the theorem. So I will consider the differential equation, the initial value problem equals x1. So I fix t0 and x1. And I want to consider the initial value problem. So let it be number 3, and this will be number 4. X prime equals f of t x, and x of t0 equals x2. But I fix x1 is fixed. And x2 will vary, but near x1. So I will not fix x2, but I will consider these initial value problems for arbitrary x2, but which is close, sufficiently close to x1. I mean that I want to consider fixed t0. T0 is fixed, is the same. So this is x1. But I want to consider all the initial value problems with the points with fixed t0, but for various x2 near x1. And the theorem will be about the following. If we start from some point x2 which is close, sufficiently close to x1, then if our function f satisfies Lipschitz condition, then the solutions will be close to each other on some interval. So these two solutions will be close to each other on some interval. Okay, so it's this. Theorem will be the following: if f is continuous and locally Lipschitz, then okay, in an open, so in an open B, so maybe let B. Then given an initial point, x1 is fixed, t0 is fixed. There exist constants beta, c greater than 0, and the interval I containing t0 such that for any x2 from such that tx2 is in D and x1 minus x2, the absolute value of this is less than beta. So for any x2 sufficiently close to x1, so they must be less than beta, we have the absolute value of x1 of t. So this is the hypothesis. These are two initial values problem, right? Two initial values problem. So x1 and x2 are two values of the solutions at the point t0. But now I want to compare x1 of t, so we may move somewhere, right? So this will be x1 of t, and this is x2 of t. So you should catch the difference between x1 and x2 without any variable, and x1 of t, x2 of t. So between these 2 points and these 2 points. So given, so if we take x2 sufficiently close x1, these solutions would be also sufficiently close. So minus x2 of t, the absolute value will be less than or equal to c times, so just c times x1 minus xt, sorry, minus x2. Well, for t in I. Okay. So we will prove this. And we will use the Granol's lemma and lemma number 1. The first lemma which was proved today was the following. So x1 of t is a solution if and only if x1 of t can be represented as x1 plus the integral from t0 to t f of s x1 of s ds, and x2 of t is a solution. x2 is equal to x2 t0 to t f of x x2 of s ds. Okay, well, then we subtract these two inequalities, subtract, and then we have the following: x1 minus x2 of t minus x2 plus the integral from t0 to t f of s x1 of s minus f of x s x2 of s ds, just by subtracting. Next, let's consider the norm. It is less than or equal to by triangles inequality plus the integral from t0 to t. This is also by triangle inequality. The norm ds. Then we can use the Lipschitz condition, apply the Lipschitz condition to the function. The function satisfies the Lipschitz condition. So this is less than or equal to L times x1 minus x2 of s, of course. And so we have the following: the absolute value of this is less than so let it be. I will move L through the integral sign because L is a constant. Okay, so this is just what we need. Can we apply the Gronow's lemma now? Let's look at the Gronow's lemma. Can we apply the Gronow's lemma? Gronow's lemma. Well, yes, with the scalar function u of t, which is equal to the absolute value of x1 of t minus x2 of t. If we denote this function by u of t, if we denote this also minus by c, let it be c. So we can see just the hypothesis of the Gronow's lemma, right? It is L times, and this is u of c. By Gronow's lemma, we have the following: u of t minus x2 of t. It is equal to u of t less than or equal to c. By Gronow's lemma, it is c, but our c is x1 minus x2 times e raised to the power L times t minus t0. but we're done. This completes our proof. Because we want to prove that there exists C, or just a moment, maybe we should let it be C bar, maybe C tilde, right? Because it is different from that C. But this constant can be bounded by, so T, maximum value of T is, so there exists I containing 0. I from alpha to beta, and we can, so if T is from alpha to beta, we can find the maximum. But maybe we can say that since T0 is between alpha and beta, then T minus T0 is less than or equal to beta minus alpha. And so this is less than or equal to e to the power L times beta minus alpha times x1 minus x2. So we're done. So this completes the proof. So we'll finish our lecture. Thank you for your attention.